Now the first unit of discrete mathematics is logic and mathematical induction. For computer science students, this unit is very important. Now, the next point is logical equivalences involving quantifiers. Now, statements involving predicates and quantifiers are logically equivalent if and only if they have the same truth value, no matter which predicates are substituted into these statements and which domain of discourse is used for the variables in these propositional functions. So, this is the notation to indicate the two statements S and T involving predicates and quantifiers are logically equivalent. Now consider the negation of a quantified expression. For example, consider the statement every student in a class has taken a course discrete mathematics. This statement is written in symbolic form as for all x px. Now here we are considering all students in a class. So domain is nothing but all students in a class. And for every student, the subject is he has taken a course discrete mathematics. So here Px as a predicate is X has taken a course discrete mathematics. And universe of discourse is the set of all students in a class. Now what will be the negation of this statement? So negation is not like that every student has not taken a course. So every student has taken a course discrete mathematics. So its negation is there is at least one student in a class who has not taken a course in discrete mathematics. So there is means there exists. So the quantifier is there exist. X not taken a course in discrete mathematics, which is negation of px. So there exists negation of px. Thus, negation of for all x px is equivalent to there exists x negation of px. Now, this is the table for negation and equivalent statements. So negation there exists x px and for all x negation px are equivalent. Same way negation for all x px and there exists x negation px are equivalent. Now what are negations of quantified statement? For all negation of quantifier is there exist. There exist for all x px. So for all it is there exist and negation of px. Similarly for all x negation px. Negation of for all x is there exists x and negation of negation is px. Then there exists x px. Negation is for all x negation px. Similarly there exists x negation px. Its negation is for all x px. Now we have seen two types of quantifiers. One is universal quantifier for all x px and second is existential quantifier. There exists x px. Now when for all x px is true, so for all x px is true if px is true for every x in the domain set. And if it is false for at least one x in the domain set, then in that case its truth value is false. Now there exists xpx. It is true if it is true for at least one x in the domain set. And if there does not exist any value x for which the statement is true, then it is false. Now there are various types of questions on quantifiers. Now see this question. Using quantifiers symbolize the following. If the universe of discourse is the set of real numbers. So domain in this case is set of real numbers. Now whatever statements are given, we have to write in symbolic form using the quantifiers for all or there exist. Now see first statement. For any real value of x, x square is at most equal to 10. Now for any it's same as for every for each. So this is given for every real number x. So here we will use universal quantifier, that is for all x belonging to R. Now what is the subject? X square is at most equal to 10. So for about x, what is given? X square is at most equal to 10. So for all x in R, we write this as x square less than or equal to 10. So this is the required symbolic form. Now second is there is value of x such that x square plus 3x minus 2 is equal to 0. Now there is value of x means the statement is given for some x, not for every x. So we use here existential quantifier. So there exists x belonging to R such that is written in bracket. What is given about x? X square plus 3x minus 2 equal to 0. So this is the symbolic form. Now, third, for any value of x, there is some value of y such that x into y is equal to 1. Now, for any value of x is for every value of x. So, for x, we use universal quantifier. There is some value of y means existence of y. So, we use here there exists y in R. And what is given about x and y? X into y is equal to 1. That we have written inside bracket. Now, fourth is there is value of x and y such that x square plus y square is negative. Negative means it is less than 0. Now, there is value of x means there is value of x and there is value of y. So, for both x and y, we use existential quantifier. There exists x in R, there exists y in R such that x square plus y square is negative means less than 0. So in this way, using quantifiers, we can express the given statement in symbolic form. Now see second example. Now here again we have to convert the given statements into symbolic form using quantifiers. Now first is all men are mortal and second some men do not like cat. Now see the first statement. It is given about men. Second is also given about men. So first here we define what is the domain under consideration. So we consider M as set of all men. Now what is given about that men? They are mortal. So we define the predicate Px as x is mortal for first case. Now as we have domain set and we have Px, now we can write it in symbolic form. Now all men means it is for each and every man. So we use universal quantifier for all x belonging to M. What is given about that x in M? X is mortal. So x is mortal means Px. So it is for all x in M, Px. Now second is some men do not like cat. Now about men, it is given that they don't like cat. So here we define Cx as x likes cat, or you can define directly x doesn't like cat. So it depends how you are define the predicate. Accordingly, you have to change the symbolic form. Now some men means there are some men. So it is existence. So there exists x in M. M is set of all men. Now, Cx is x likes cat and here it is given as don't like cat. So, we have to consider negation of Cx. So, there exists x in M such that negation Cx. Now, instead of defining x likes cat as Cx, if you define Cx as x does not like cat, then in that case, instead of negation, you can write directly Cx. So, in this way, we can convert the given statement in symbolic form using quantifiers. Now see third example. Let Px, x can speak Russian, Qx, x knows the computer language C++. Now here some statements are given. Now using quantifiers and logical connectives, we have to express it in symbolic form. Now here the set of domain is given as set of all students at your college. Now see the first statement. There is a student at your college who can speak Russian and who knows C++. Now see, there is a student means this is existential quantifier. So we use here there exists X. Now what is given about that student? He can speak Russian. He can speak Russian means Px. He knows C++. It means QX. So we have to write PX, QX. But logical connective and is used here. So PX and QX means there exists X such that PX and QX. That is the symbolic form. Now second, there is a student at your college who can speak Russian and who doesn't know C++. Again, there is a student at your college is nothing but there exists X. Can speak Russian is PX. and its conjunction. Doesn't know C++ is nothing but negation of QX. So the symbolic form is there exists X, PX, and means conjunction negation QX. Now third, every student at your college either can speak Russian or knows C++. Now here it is given about every student in your college. So every student means for all. So we use the quantifier for all X. Now what is given? Can speak Russian, PX, or knows C++. So it is PX or QX. So this is for all X such that PX or QX. Now fourth, no student at your college either can speak Russian or knows C++. It means there is no student at your college who can speak Russian or knows C++. So actually no student means this is given about all students at your college that they don't know Russian and or C++. So how to write in symbolic form? For all X, so they don't know Russian as well as C++. So for all X, no Russian, negation of PX. At the same time, no C++ means negation of QX. And it is and. Even though it is given as or, it means actually they don't know either Russian or C++. It means they know neither Russian nor C++. So we have to consider negation of both together with and. So the symbolic form is for all x negation px or qx, which is same as for all x negation px and negation qx. So no student at your college either can speak Russian or knows C++. Now, one more. Translate the given statements into logical expressions using predicates, quantifiers, and logical connectives. And then we have to write negation of each. Now, in some examples, they define the predicate. But if it is not defined, then we have to define that. Again, if the domain is not defined in that case, we have to define domain. Now see first, all roses in the garden are either pink or white. Now this statement is given about roses in the garden. So we consider domain as G, set of all roses in the garden. Now what is given about roses? Either pink or white. So for pink we define one predicate and for white we define another predicate. So Px is suppose X is pink. Wx is suppose X is white. You can define Px or Qx also. But if I define P and W, immediately I understand that P for pink and W for white. So Px and Wx we have defined. So now we have domain as well as predicate. So we can write in symbolic form. So this is given for all roses. So we use quantifier for all x in G. Now what is given? Px or Wx. So this is Px disjunction Wx. Now we have to write negation also. Now already we have seen how to write negation of quantifiers. Now for all x, instead of that, negation is there exists x in G. And we have to write negation of Px or Wx. And for that we use De Morgan's law. So negation of bracket Px or Wx. So this is equivalent to there exists x in G such that negation of Px or is replaced by and negation of Wx. So this is the negation of that symbolic form statement. Now second, for some real numbers x and y, x square minus y raised to 4 is negative. Now again here it is given about real numbers. So we consider domain as real numbers. But for real numbers standard notation is there, that is R. So it is not necessary to define that state separately. Directly you can write. Now what is given for some real numbers? So we use here existential quantifier. There exists x, there exists y in R such that x square minus y raised to 4 is negative, means less than 0. Now we write its negation. So again negation of there exists is for all. So it is for all x, for all y in R. Now what is negation of less than 0? Not less than 0 means it may be greater than 0 or equal to 0. So it is for all x, for all y in R, x square minus y raised to 4 greater than or equal to 0. Now next example. Now here already we have given some statements in symbolic form using quantifiers. Now we have to write in English. Let Px be the statement x spends more than 5 hours every weekday in a class, where the universe of discourse is set of all students. Express each of these quantification in English. So here domain or universe of discourse is nothing but students. Now first is there exists xpx. Now, there exists x means there is some student. Now, what is given about that student? It satisfies what? Px. So, how can we write in English? There is a student in a class who spends more than 5 hours every weekday in a class. Now, see second. For all x, px. So, for all x means it is given for every student x in that class, that it satisfies px. So how to write in English? Every student or each student in a class spends more than 5 hours every weekday in a class. Now, third, there exists x negation px. So there exists x means there is a student, and here it is given as negation of px. There is a student who does not spend more than 5 hours every weekday in a class. Now last, for all x, negation px. So for all x means this is given about all students, that negation of px. So it means that there is no student who spends more than 5 hours every weekday in a class. It means no student spends more than 5 hours every weekday in a class. So in this way, question can be asked in this way also, that express the given quantification in English. In previous problem, we have given it in English and then we have expressed them in symbolic form using quantifiers. Now again, this is same type question. So here Cx is given as x is comedian and fx is given as x is funny. Now the given statements in symbolic form we have to express in English. Now universe of discourse is the set of all people. Now see, this is for all x, Cx implies fx. So for all x means this is given for each person, for every person in that group of people. If Cx, then fx. Now if Cx, then fx means if x is comedian, then x is funny. It means if some person is comedian, then definitely it is funny. But this is given for all x in that group. So we can say that every comedian is funny. Means any person who is comedian is funny. That is the statement in English. Now B, for all x, Cx and Fx. Now for all x means for every person, Cx as well as Fx means every person is comedian as well as funny. So how to write in English? Every person is comedian and funny. Third, there exists x, Cx implies Fx. Now again this part is same but the quantifier is different. So there exists some x who is comedian, then he is funny. So how to write in English? There exists a person such that if he or she is a comedian, then he or she is funny. Now D, there exists x, Cx and Fx. Now this is similar to B part. Only thing is instead of for all x, the quantifier is there exists. So instead of writing for all persons, we write there is a person or there exists a person who is comedian and funny, because here Cx and fx. So we combine cx fx by using logical connective and. Now, here already some statements are given in symbolic form using quantifiers. Now we have to write negation of each, means negate the following statements. Now remember, negation of for all is there exist. Negation of there exist is for all. Now first is for all x there exist y, x plus y greater than xy. Now, negation of for all is there exists x. Negation of there exists y is for all y. At the same time, we have to consider negation of this predicate, that is x plus y greater than xy. So not greater than means less or equal. So negation of this part is x plus y less than or equal to xy. Now, second is there exists x for all y, x square plus y square plus 2 is equal to 0. Again, there exists x, negation is for all x. For all y, negation is there exists y. And for equal to, its negation is not. So, x square plus y square plus 2 not equal to 0. Now, third, there exists x for all y, x plus y less than or equal to xy. So its negation will be for all x, there exists y. Now not less than or equal to means greater than. So x plus y greater than xy. Now fourth, for all x there exists y, x square plus y square plus 2 not equal to 0. So negation is there exists x for all y, x square plus y square plus 2. Not means equal. So x square plus y square plus 2 is equal to 0. So in this way, given statement in symbolic form, we can write its